start. In the first half of this course, we've seen different approaches used to both analyze and design error correcting code. Right, so we started off with some bounds on the size of error correcting codes using some combinatorial approaches. So you can think of that as combinatorial coding theory. And then we switched gears. We looked at some abstract algebra. We defined rings, fields, how to construct finite fields, and algebraic error correcting codes, that is Reed-Solomon codes and Reed-Muller codes. Right, so these are what are called algebraic error correcting codes, sometimes also called classical error correcting codes. So now we look at a completely different approach towards error correcting codes, and that is constructions based on graphs. So some of these are also called modern codes in some sense. As we saw, even the codes that we've seen so far, including Reed-Solomon codes, they're optimal in some regard, right? Because generalized Reed-Solomon codes are maximum distance separable, so they achieve the singleton bound. Right? So in some sense they are optimal, but then if you want to, let's say, design a code for transmission over the AWGN or over the BSC or the BEC, we still don't know how to construct codes which achieve the capacity or achieve rates close to capacity, right? Both Reed-Solomon codes and Reed-Muller codes and any of the codes that we've seen so far, they don't really approach capacity. Okay, so they achieve some particular bound, but no better than that. And that was indeed the state of affairs for a very long time, up to say at least the early 90s. People didn't know how to construct error correcting codes that could be efficiently encoded and decoded and still achieve the capacity of any non-trivial channel, right? Whether it's the BSC or the BEC or the AWGN channel, nothing. So at least people thought that, okay, this channel capacity is in some sense just a theoretical limit, and it's not really possible to achieve codes which actually get you close to capacity. Right? But then in the we also seen concatenated codes, which at least in principle lets you get close to capacity, and the encoding and decoding complexity is small, but that requires you to go to very, very large block lengths, and even though it is polynomial time, the polynomial kicks in only for like very, very, very large n. So although in principle you can get to capacity using polynomial time encoding and decoding algorithms, it's not really a practical scheme. But then in the early 90s, a new class of codes came up. These are based on convolutional codes. These are called turbo codes, and essentially use two convolutional codes with some sort of feedback going from one to the other. And surprisingly, I mean, the inventors of turbo codes, they didn't give a proof or anything. They just said, this is how you construct a turbo code, and then we did some simulations, and you can approach rates close to capacity and still achieve very small probability of it. That was a landmark result. People initially didn't believe this, but then it turns out that turbo codes indeed get you close to capacity. And till date, of course, there's been a lot of analysis of turbo codes done so far, but a complete proof that turbo codes achieve capacity still open. People don't know how to prove this. And then later on, there was another class of codes which was invented way back in the 60s, called low density parity check codes. Even so LDPC codes or low density parity check codes, these were known to approach capacity, but only with maximum likelihood decoding, which takes exponential time. There were some low complexity algorithms known, but then they never got you close to capacity. So in the early 2000s, there was again a resurgence in the study of LDPC codes, and it turns out that people were able to show, at least prove to some extent, that there exists a very low complexity decoding algorithm for LDPC codes, and that actually gets you close to capacity. Right? So these were sort of two major classes of codes. the so-called codes based on graphs, which are capacity achieving. In fact, LDPC codes can approach the capacity of any binary input memoryless symmetric output channel, not just BSC or BEC. You can construct LDPC codes that achieve the capacity of any channel, and for that you also have a low complexity decoding algorithm. Now there are some caveats as we'll go along. We'll see how do we construct LDPC codes, what is required to construct a good LDPC code, and how do you analyze the performance of low complexity decoding algorithm. But even then, things are not so straightforward. There are some minor technicalities. There are some assumptions that need to be made in order when we say that these approach capacity or achieve capacity. So these are the two classes of codes that we'll see in the next few classes. I won't really touch upon turbo codes in much depth, but I will talk about convolutional codes, the basic building block used for turbo codes, and then we'll go into much more in-depth discussion of LDPC codes, because they are indeed they're being used in current standards today. Turbo codes, again, those are the first class of capacity achieving codes, but then they're not as good as LDPC codes or another class of codes called polar codes, which are also introduced in standards today. Okay, so but as it turns out, convolutional codes, LDPC codes, all of these can be studied in a very broad general framework. There is one broad technique or class of techniques which lets you systematically come up with low complexity algorithms for a very large class of codes, and not just low complexity decoding algorithms for codes. This sort of general approach encompasses a wide variety of algorithms used in other fields as well, including statistical inference or even the fast Fourier transform. Turns out that we're going to see one general approach which also includes the fast Fourier transform, decoding LDPC codes, decoding convolutional codes, decoding turbo codes, and performing inference on graphs. And all of these are special cases. So first, even before we go to all of that, let's first quickly recall what we've seen so far, some general principles. Yes. Yeah. Yes. So the rate must be close to capacity. We want codes that have rates for asymptotically large n. They have rate close to capacity and probability of error that is arbitrarily small. Right? So the general problem is as follows. For sufficiently large block lengths, we want to construct, in some sense, explicit codes with polynomial time encoding and decoding. In fact, not just polynomial time, we'll want them to be just order, worst case order n square, but we'll demand even smaller than that, most order n log n or n times polynomial in log n. Okay, so it must be much smaller than order n square. We want the rate equal to, let's say, capacity minus some epsilon. So there's a target rate which is very close to capacity, and the probability of error should be less than or equal to whatever target probability of error you fix, maybe 10 to the minus 5. In general, we may want this to be either exponentially decaying in n, or maybe even polynomially decaying. Say order 1. So more importantly, we want a practical scheme, right? We of course want to analyze the scheme theoretically. At the same time, we should be able to build these and deploy them on chip. That's what is more important for us right now. Okay, and in fact, the first class of codes, again, not capacity achieving or even optimal in any sense, but the first class of codes which were used in practice are the so-called convolutional codes. These are fairly decent. These were the best things that were known apart from Reed-Solomon codes. So Reed-Solomon codes were very good, but the problem is, again, you need large field sizes, which translates to reasonably large complexity. So when you're trying to implement channel codes on very low cost hardware, or again think back to the 90s, right? VLSI was not so well developed at that point in time. You could not implement very complex algorithms. Power, you can't consume too much power on chip, right? So even order n square complexity is too much. The best that you can hope for, the best that you can implement on chip are algorithms which have complexity, say order n or maybe order n log n. Anything more than that is you cannot implement. Today, of course, chips are much faster, and we don't have to think so much about the complexity. Of course, you still can't implement anything more than order n square for most practical purposes, but even order n square is reasonable today. But then back in the 90s or late 80s, order n square is too much. You can't implement, right? So the class of codes that we've seen so far are what can be broadly called block codes. Right? That is because what did we do first? We first fixed the block length, right? And the encoding was a mapping from a sequence of k bits to a sequence of n bits. Now, if you want to transmit more than let us say k bits, then you can't do it. You'll have to redesign the entire code, right? If I want to transmit k plus 1 bits, then I have to redesign everything from scratch. I have to use a different code. The code that I designed for block length n cannot be used for block length, cannot be used for, let's say, more than k bits, right? So we've seen block codes and more specifically linear block codes. And in this case, essentially encoding is linear, and more specifically just matrix multiplication. Right. Another approach to designing codes is the following. Instead of, again, encoding is a linear operation, right? So if you want to design a scheme with a low complexity encoder, obviously we would look for linear operations, right? Nothing more than linear. But then now we don't want the block length to be fixed, right? Because sometimes you may want to transmit 10 bits, sometimes 100 bits, maybe, or sometimes, let's say, 10,000 bits. And you want a single scheme that works for all these cases. In any communication system, let's say voice communication, you don't really know how many bits you're going to transmit before. So one way to do it is you have, now we've seen how to construct linear block codes. One way to sort of address this problem of varying number of bits is to not fix is to maybe have 2 or 3 different codes of different block lengths. Depending on how many bits you want to transmit, you pick the block length which is most suited for you, and then use that code to encode. That's one approach. But then back in the 80s or so, people thought of a different approach. So instead of using a linear block code, you use what is called a stream code, sometimes called a stream code or a convolutional code. So in this case, again, encoding is a linear operation, but you view this as, let's say, a filter. Right? Now, the input or the message is now a sequence of bits, right, or a sequence of symbols. You can view this as a discrete time signal, right? So the message is, you treat this as a signal. Let's call it m of t. So this is a discrete time signal. And the code word, now again, it does not necessarily have to have fixed length. It could be maybe variable length. So the code word is another signal which is some other discrete time signal. And how do you go from the message to a code word? Using some kind of a filtering operation. So again, at that point, signal processing was fairly well developed. There is a good theory of filters. So why not use filters to design a good channel code? So encoding is basically filtering. So you have m of t, you have an encoder which essentially corresponds to defining the impulse response of system, and you get the code word. So your encoder is basically a linear time invariant system. Right? So depending on the structure of the impulse response, these are categorized into various different forms. I won't talk about all of them, but the first that we'll talk about are what are called non-systematic feed-forward convolutional groups. So this feed-forward essentially means that the impulse response is basically a finite impulse response. Right? So You can implement this using just feed forward elements, and there's no feedback. It's not an IIR filter, it's an FIR filter. So let's maybe take some example. So suppose I have M of t. Let us say that T of t is say delta t plus delta t minus 1 plus delta t minus 2. Now again, remember that we're transmitting a sequence of bits, and we need to add some redundancy. If we're just transmitting one stream, if the input is one stream and the output is just one stream, there may or may not be some redundancy. So instead what we do is the input is one stream of bits, the output can be viewed as a stream of two streams of bits concatenated with each other. So you can define two impulse responses, G1 of t and G2 of t, in this particular form. So the code word in fact consists of two streams, which is so C of t would in fact be C1 of t and C2 of t, which is M of t convolved with 1 of t, and C2 is M of t convolved with C2 of t. Okay. So in this case, what can you say about the rate of the code? Suppose I have a system of this particular form, right? The input is an infinite sequence of bits, right? So M of t could be of infinite length. The code word is sort of two sequences, again both of infinite length. So intuitively, what do you think the rate of this code would be? 1/2, right? Because you have one input stream and two output streams. So it's natural to say that the rate of this code is so if you take any two integers a and b, the rate a by b convolutional code consists of a input streams and b output streams. So m1 of t, m2 of t, and so on up to ma of t and b output stream. T1 of t, T2 of t, Tb of t, again, since there are A input streams and B output streams, so for every combination you need an impulse response, right? So there are a total of A times B impulse responses, So let's call them G11, G12 up to G, so on up to GA. So GIJ is the impulse response. Sometimes called the generator sequence. For input I and output J. And what is Cj of t equal to? So Cj of t is going to be G1 J t convolved with M1 of t plus G2 J t convolved with M2 of t, so on. Gaj of t convolved with Ma of t. So you can view this as a series of filters. So let's say I have M1t, M2t up to MAT. All of these one, 2, 1, so on to A1. So take all of these, add them up to get C1. Right, so there are a total of A input streams. There are a total of A times B filters, right? And a total of B output streams. Right? But again, one thing to keep at the back of your mind is that all of these operations, they're not done over the reals, right? They're done over some finite field. Any questions? Correct. So again, there are different ways of implementing these. So for example, let's take one example which is a rate 2/3 convolution. Okay, so in this convolutional code, you have M1 and M2, and you have C1, C2, and C3. In this case, C1t is exactly equal to M1 of t. Okay. C2t is exactly equal to M2 of t. Okay. Now C3 of t is some combination of M1 of t and M2 of t, and in this case, let us say C3 of t is M1 of t plus M1 of t minus 1 plus M1 of t minus 2 plus M2 of t plus M2 of t minus 1. Okay. So how do you go from M1 of t to M1 of t minus 1? Yeah. Yeah. Delay, right? You need a delay element. So basically what you need is a shift register. So you have one delay element. So what is the maximum delay that is required for M1? 2. What about M2? Right, so you need a total of 3 delay elements to implement this particular convolution code. So this is at least the encoding part. Right? Okay, but remember that for linear block codes, the generator matrix for a given linear code is not unique. Right? You can have the same code, but multiple generator matrices for the same code. In a similar way, you can, even for a convolutional code, the generator sequence is not unique. You can have different ways of constructing the same convolutional code. So in this case, this required 3 delay elements. But it's also possible to construct this using just two delay elements. How do you do that? So here is one such construction. You take M1, M2 of t. So we can instead group together elements which have the same delay, right? And then add up those which require a certain amount of delay. So there's one with delay 2, right? What is at the output of this will have delay 2, right? So take M1, feed it to this particular delay element. You have M1 of t minus 1 plus M2 of t minus 1. So I'll put an adder element over here. I need an M1 of t and M2 of t. So this is my C3 of t, right? So this gives me exactly the same code. There's no difference at all. But now this has fewer number of delay elements. So depending on your application, you may want to prefer this particular code over this particular code. Sometimes even for analysis, one particular code or one particular encoder may be more easier to analyze than the other. Okay. So in this case, in this particular form, right, what are we doing? For each, you group together elements corresponding to one particular message, put the number of delay elements that you require, and then at the end add them all up, right? So in this particular approach, the number of adder elements is exactly equal to the number of output streams, right? So for each output stream, you may have one adder element, at most one adder element. In some cases, you don't need any. And the number of delay elements is the total number of whatever, at most the total number of terms in the impulse response. Correct? So for each of the input streams, you have a separate shift register. So this is sometimes called the controller canonical form. Again, just terminology. Whereas in this particular approach, the total number of delay elements is exactly equal to the maximum delay. You don't need any more, irrespective of the number of input streams, right? And the total number of adder elements again now could be different. It depends on the number of, again, it's exactly equal to the number of delay elements, right? After each delay or before each delay element, there could be one or multiple such input streams, adder elements. So this is called the observer canonical form. And both of these are terms which come from control systems, by the way. observer canonical forms and controller canonical. And of course, I mean, all of these have roots in filters and control systems and so. Right? So we're basically using ideas from signal processing and control systems and trying to use them to design codes. Unfortunately, however, these don't have very good minimum distance, and in general, these are not capacity achieving. Right? At least by themselves, they're not capacity achieving. But you can block together convolutional codes. You can group together different convolutional codes and then do some more operations in between, and still end up with a good capacity achieving code. So in this case, what does the capacity of the, sorry, what does the complexity of encoding depend on? Correct. Which in turn depends on the length of the impulse response. Right. So depending on the maximum delay, the complexity increases. Right. So irrespective of the block length, right, irrespective of, let's say, the length of the input stream, the complexity now depends only on, of course, it of course scales linearly with the number of input bits. But then let's say that you use a filter of constant length, then the overall complexity is just linear. Now no more than linear, right? Which is very good. Now you have a linear time encoding scheme, but of course we don't know how to decode this yet. You need to perform some operation at the receiver, some kind of decoding algorithm, and it may seem that decoding is now complicated. We've made encoding very simple. It's just simple filtering. But now, are we paying a price in terms of decoding complexity? Turns out that, again, if you use filters of constant length, decoding can also be performed very efficient. So there are two different decoding algorithms, one called the Viterbi algorithm and another algorithm called the BCJR algorithm, which are both optimal in certain respects and can be used to decode convolutional codes very efficiently. I won't introduce the Viterbi algorithm and the BCJR algorithm separately. We'll get to that, but instead of explaining what the BCJR algorithm is, what the Viterbi algorithm is, and so on, we'll now look at a very general approach of systematically constructing many such algorithms. And all of this comes from a very general rule called the Generalized Distributive Law. So what is a distributive law? Yeah. Okay, so A times B plus C is equal to AB plus AC. Right? So that's what you know about the distributive law. And this holds not just for addition and multiplication, but in general for any finite field, for any field for that matter. So the generalized distributive law tries to generalize this beyond fields. In fields, you have an addition operation, a multiplication operation, and you required a lot of other properties, right? You wanted the existence of identities, inverses, and so on. Now, is it possible to just keep the distributive law, keep the minimum set of properties that we require? Again, the goal is to be able to construct algorithms for various purposes, whatever that means, and still keep the bare minimum set of operations and still keep it useful, right? And that's the approach used for the generalized distributive law. Now again, all of these algorithms that I'll be talking about, they were constructed separately, right? So someone invented the Viterbi algorithm for decoding convolutional codes. The BCJR algorithm again was invented for decoding block and convolutional codes. We'll see some codes to some algorithms to decode LDPC code. So all of these were constructed separately, but it turns out that the generalized distributive law is a systematic way of getting all of these algorithms using a single shot. Right? And why is the distributive law particularly important? So let's maybe just quickly see an example, okay, as to how the distributive law can be used to get savings in terms of complexity. Now, suppose I have the following problem. Okay, I have two functions, let's say f of xy, and I have another function, let's say g of y comma z. Okay, these are two different functions are defined over where x comes from some alphabet script x, y comes from some alphabet script y, and z comes from some alphabet script z. These are all finite alphabets. My goal is to compute the following quantity. It is, I want to find the summation over all x, y, z, f of x comma y times g of y comma z. Okay, how many arithmetic operations do I need to compute it in this particular? How many terms do I have? Yeah. So size of x times size of y times size of z, right? So this is what is sometimes called a sum of product term, right? Right? And how many product terms are there? The number of product terms is size of x times size of y times size of z. Okay? For every term, I have to perform one multiplication. So the total number of multiplications is size of x times size of y times size of z. And once I do all of these multiplications, I have to add all these terms together, which is total number of terms minus 1. Right? So I have size of x times size of y times size of z minus 1. So right now I'm just counting both addition and multiplication as sort of taking the same complexity, but whatever it is, the total complexity is linear in or some constant times size of x times size of y times size of z. Okay. is it possible to compute A using fewer number of operations? So here you should assume that size of x, size of y, and size of z are very large. Let's say 100 or let's say 1000. Okay. So in this case, the total complexity would be 1000 cubed, which is enormous. That's 10 to the 9, roughly, order 10 to the 9. Is it possible to have a much greater reduction? The advantage over here is that f and g, they're not both functions of x, y, and z. So f depends only on x and y, and g depends only on y and z. So let me try to use the distributive law over here. Right? So in particular, so let's take A, which is, let's first keep, instead of summing over x, y, and z, let us take summation over y outside, summation over x, f of x, y, times g of y, z. Right? Now, the summation, when I'm summing over x, the second term is not really helping me. Similarly, when I'm summing over z, the first term doesn't really matter. Right? So I can take, when I'm performing summation over x, I can take this term outside the summation. Similarly, for this, I can take this entire term outside the summation over z. So this is just summation over all y of summation over x, f of xy, times summation over z, g of y. Right? Now let's count the number of operations required. Now for each y, how many additions do I need to do to compute this? So this requires, I have to do size of x minus 1 operation. For each y, I need to perform size of x minus 1 additions. And how many additions over z? Size of z minus 1 and 1 multiplication. Right? So for each y, I need to perform size of x minus 1 additions, size of z minus 1 additions, and 1 multiplication. So the total number of operations required for each y is size of x plus size of z minus 1 plus 1. Assuming that addition and multiplication would take the unit time, or have the same amount of complexity. You agree? Okay. So this is the total number of operations for each y. So what is the total number of operations required? It is this times the size of y. So the overall complexity is size of y, whatever, some constant times size of y times size of x plus size of z. Constant terms. So from complexity size of x times size of y times size of z, we've gone down to complexity size of y times size of x plus size of z. So once again, now if all of these have size, let's say 10 to the 3, then the overall complexity is now some constant times 10 to the power 6, which is huge savings. And all we did was basically use the distributive law. So we had summation, you have AB plus AC, you write it in terms of A or A times B plus C, you somehow magically get fewer number of operations. It can be seen right here, right? So here you have 2 multiplications and 1 addition, whereas in this case I have 1 addition and 1 multiplication. So is it possible to do this in a systematic fashion? And what does it give us? Now again, we assume that we're operating over some field, right? But can we even generalize this further? We don't really require all the properties of the field, right? We need to be able to add, we need to be able to multiply, but we don't really care if we can divide or not. We don't really care if we can subtract or not. In certain applications, it doesn't matter. So let's try to focus on algebraic objects that let you do only this minimum set of operations. So this is what is sometimes called a commutative semiring. We've seen fields, we've seen rings. Right? We saw that the set of polynomials forms a ring. When in going from a field to a ring, we just discarded the division operation. Right? Inverses don't exist. Now, right now we will discard both the additive inverse as well as the multiplicative inverse. Again, we're going to assume that both addition and multiplication are closed. And in addition, under addition, this forms a commutative monoid. Basically, it is commutative, associative, the identity element exists, but inverses may or may not exist. Similarly, even under multiplication, It is a commutative node. So again, multiplication is commutative, multiplication is associative, and there's a unique multiplicative identity. In addition, we of course, want the distributive law to hold. So obviously, every field is a commutative semiring. Every ring is every commutative ring is also a commutative semiring. So, for example, set of all polynomials, real numbers, rational numbers, all of these form commutative semirings. Integers, all of these. Right, so let's see some more interesting examples. So, what if I now consider A to be the set from 0 to infinity, including infinity? This includes a special element called infinity, whatever that is. And under standard addition and standard multiplication, does this form a commutative semiring? It's commutative both under addition and multiplication. It's associative under both addition and multiplication. The additive identity exists, the multiplicative identity exists, and it is distributive. So it is. What if it were the open interval 0 to infinity? It would not be, because there would be no additive identity. Okay, so once again, I'm going to take 0 to infinity, but now I'm not going to take addition and multiplication. I'm going to take the min operation and standard multiplication. So the minimum is a binary operation. Given any two inputs, it returns the minimum of those. Is this commutative? Is the min operator commutative? It is. Min of a comma b is min of b comma a. Is it associative? The min of a comma b comma c is the minimum element, so it doesn't matter whether it's abc or cba or cab. Right? Okay. Is there an identity element? We want some element, let's call it I, such that I comma min of I comma x equal to x. infinity, right? So min of infinity comma x is always equal to x. So the additive identity in this case is infinity. Again, I'm using additive identity. Let me call it identity 1 instead. Is plus infinity. What about the second operation? Again, it's standard multiplication. So in this case, the identity is 1. Again, it is closed under, it's closed, it is commutative, multiplication is commutative, multiplication is associative, and there's an identity. Oh, now what about distributive? So we want to verify that A times min of B comma C is equal to min of AB AC. Yeah. Yes. It is distributive. Okay. So this is indeed forms a semiring. This is sometimes also called the min sum semiring. What about this side? Why? Yeah. So if you take a negative number A, then A times min of B comma C is not necessarily equal to min of AB and AC, particularly if yeah, B and C. Okay, so now let's take the same set 0 comma infinity, but instead look at max and product. Is the max operator commutative? Yes. Is it associative? It is. What about identity? What about the second one? Yeah. Yeah. Is it distributive? Again, since we're only looking at non-negative numbers, max of AB comma AC is equal to A times max of B comma C. This is called the max product semiring. Let's say the first operation is the minimum, second operation is addition, real addition. So remember, in the distributive law, you can't exchange the two operations. This is a first operation, this is a second operation. In a field, the first operation is addition, the second operation is multiplication. Whereas in this case, the first operation is minimum, the second operation is addition. So if you look at the distributive law, what we're saying is that A plus min of B comma C is equal to min of A plus B comma A plus C. We are not saying that min of A comma B plus C is equal to a min of A comma B plus min of A comma C. Right? So these two are not the same. In this case, the first operation is the minimum, the second operation is addition. Okay, so is this a semiring? Is the min operation is commutative again? What is the identity again? Both of these are monoids. They're commutative monoids. We've just seen both the min and addition. All that needs to be checked is the distributive law, and A plus min of B comma C is min of A plus B comma min A plus. So it is. And this is sometimes called the min sum semiring. Yeah, this one over here. This is min product, right? So this is also min product. Sorry, that means sum. So the min product. So this is standard multiplication, the min product semiring, and this is the min sum semiring. Okay, so now this is a different set. Again, max product. Is this a semiring? So first, again, is it commutative? Yes, commutative associativity is true for both. What are the identities? Yeah, are you sure? Look at the set. It is minus infinity. The second identity again is multiplication, so the identity is 1. Now we want to check whether max of A times x of b comma c is equal to x of ab comma ac. Yeah, it doesn't. Why? Yeah, so if it's a negative number, so let's say minus 2 times max of 1 comma 2, this would be equal to minus 4, whereas max of minus 2 comma minus 4 would be, right? Okay, let's take one last example, and that is, okay, so take k equal to 0 comma 1, and the addition operation is or the first operation is or and the second operation is and. Is it commutative, associative? Identity 1, what is the first identity? The second identity is 1. Is it distributive? It is. So this is also semi. Okay, so let's stop here. Time for the next class.